For the following section, we're going to be talking about transformations and translations that occur on graphs. So the idea with transformations is when you take a graph and you want to get a general idea of what it looks like without plotting a bunch of points, then all you have to do is know what the parent or base function looks like, and then you can just shift it around from there to see what the actual graph you're looking for looks like. For instance, every graph that contains an exponent of x squared and it's just a polynomial will look like a parabola. It will just be shifted around in some way like so. But they will all have the same general shape. So, as long as we know what parent function we're dealing with, we can move the parabolas around to get an idea of what function we're dealing with, what the function looks like, that is. So, the first couple of transformations we deal with are vertical and horizontal shifts. So we say a vertical shift occurs outside of the function. So given y equals f of x, just some standard function, then y equals f of x plus k, meaning we're adding some constant k to the outside of the function, means that the function f of x has been shifted up k units if k is positive, meaning it's greater than 0, or down k units if k is less than 0 or negative. So if you add or subtract some constant number like 5 or negative 15 to the outside of a function you started with, like x squared for instance, then that just means you are moving the graph up or down that value of 5 or 15, depending on whether it's positive or negative. A horizontal shift works almost exactly the same way, but a horizontal shift occurs inside of the function. So if you're given y equals f of x, then y equals f of the quantity of x plus h is a horizontal shift. Notice the constant is now being added inside of the function, within it. And we say that this means f of x has been shifted to the left h units if h is positive, and to the right h units if h is negative. So it's the opposite of what you would think for a vertical shift. Vertical shift, if it's positive it goes up, if it's negative it goes down. But with a horizontal shift, if it's positive it goes to the left, if it's negative it goes to the right. Okay, so let's see what this actually looks like when we're graphing here. We have the following example where we want to sketch f of x equals the absolute value of x. We'll go ahead and put that in red. Then we have g of x equals x plus x plus 4 inside of an absolute value. We'll put that in green. And finally, we have h of x equals the absolute value of x plus 4. We'll put that in blue. So f of x is our parent function. It's the standard function with nothing being added, subtracted, or multiplied to it. So what does the absolute value of x look like? Well, hopefully this is something that you've seen in the past. It's just a V shape. You could quickly check this by just plotting a few points, but this is one of our standard graphs. It just looks like a parabola, but instead of a U, it's a V. So we'll go ahead and label this f of x. And now from here we want to graph g of x, which is the absolute value of x plus 4. That plus 4 is inside of the function though. And because it's positive, it means it's going to go the opposite way of what we're thinking. So just a reminder, if it's inside of a function, it's a horizontal shift. If it's outside of the function, it's a vertical shift. And this is true with any of these transformations we come across. If it's inside, it's horizontal. If it's outside, it's vertical. So we already know this is going to be horizontal, either left or right, and because it's positive, our rule says when it's positive, we go to the left. So this graph has been shifted to the left 4 units. So if we take this parent function and we make 4 tick marks, then we redraw exactly what we have here. Try to match the slope. Notice these two are parallel, and now match this slope. These two are parallel. And notice we have the exact same graph. This left side is a little bit shorter, but because it has an arrow, it's the same thing. I'll go ahead and draw it a little bit longer though to make it a little bit easier to see. It's the same graph. And now this shows us that g of x is just a horizontal shift of the original function f of x. It's the exact same graph, just moved to the left 4 units. Now let's do the same thing with h of x. Take a moment, see if you can graph what that would look like. Okay, so trying it together, we have the absolute value of x plus 4. Because the 4 is being added on the outside of the absolute value, that means it's going to be shifted vertically. And because it's being added, that means it's going to go up. If it were subtracted, it would go down. So it goes up 4 units. So we'll start at 0. 1, 2, 3, 4. And we're going to take this V shape and just draw it back up here. Again, try to make the lines parallel so it shows you're dealing with the same graph. And this is our graph of h of x. It's the exact same V shape, or the absolute value graph, but it's been shifted up 4 units. Okay. So from here, we can introduce our next type of transformation. And this transformation says given y equals f of x, then y equals negative f of x, meaning a negative times f of x, represents a vertical reflection. Notice the negative is being multiplied to the outside of the function. That means automatically it's vertical. And then it represents a reflection whenever you multiply by a negative. So what does a vertical reflection mean? Essentially, these are 2 ways to think about it. All of the y values are going to change signs. So if your original point had a y value of -2, it now has a y value of +2. Another way to think about it is the x-axis, meaning this axis, is a mirror. Anything above it will flip below it, anything below it will flip above it, and anything that was on the x-axis will stay exactly where it is. So with that, let's go ahead and sketch f of x equals x cubed and g of x equals negative x cubed in the same plane. So the graph of x cubed is again hopefully something we have committed to memory. If not, if you just plug in some points or look at it on a calculator, you'd be able to get a general idea. It essentially looks like if you took a parabola and you kept the right side the same, but then you flipped the left side down. So picture if we had flipped this back up, it would look like that, which is basically a parabola shape. But instead we've flipped it down. That's our graph of x cubed, so that's our graph of f of x. So we're graphing f of x in black. We'll go ahead and graph g of x in red. So g of x is negative x cubed. So we don't have to go through plugging in a bunch of points for x to get an idea of what this graph looks like, because we know when you multiply by a negative, it just represents a vertical reflection, as long as that negative is on the outside of the function. Notice the negative is not contained within the cube. Otherwise, this would be a horizontal reflection, which we don't really get into in this section. So, with this, if we look at this graph, remember a vertical reflection means your x-axis is like a mirror. So, this point lies on the x-axis. That means it's going to stay exactly where it is. Another way to think of that is this point represents y equals 0. What happens if you multiply 0 by a negative? It's still 0, so it didn't move. Okay, from here, below the x-axis, so all these points on the left side of the y-axis here, this entire side is going to get flipped up because the x-axis is now a mirror. So this entire left side is now going to look like this. And this entire right side that is above the x-axis is going to flip below it and look like this. So we've just created a mirror effect from our original graph. The bottom flipped up, the top part flipped down, and this gives us our graph of g of x, which represents a vertical reflection of the graph of x cubed. Okay, so continuing from here, we now say given y equals f of x, then y equals a times f of x represents a vertical, and we have two cases here. It represents a vertical stretch if a is greater than 1. And it represents a vertical shrink or compression, two names for the same effect, if a is between 0 and 1. Notice we're missing some cases here, so I'll just quickly cover those. We don't have to worry about a being equal to 1, because that would just give us the exact same function we started with, f of x. We don't have to worry about a being 0, because then that would just change the function to y equals 0, which would just turn it into a horizontal line. And we don't have to worry about when a is negative, because that's already taken care of in the vertical reflection case. If a is negative 2, then that means there is a vertical reflection and a vertical stretch because of the 2. Alright, so with that, what does this mean to us? Well, a vertical stretch literally means if you have a graph that's this tall, for instance, then when you vertically stretch it, it's going to look like this. You pulled your y values apart. And when you vertically shrink or compress it, this original graph will look like this. It's been compressed together. The y values are now shrunk. So, with the following example, we're going to show a basic case of how this works, but then I'll show a more complicated example to explain why a certain effect might look like it's happening, but it's not really happening. So, let's go ahead and start with this. We want to graph f of x equals x squared. Our parent function is the parabola. We'll put it in black. Then g of x equals 2x squared. We'll go ahead and put that in red. And then h of x equals 1/2 x squared. We'll put that in blue. To graph f of x equals x squared, we know that that's just a parabola. So it's going to look something like this. Just a U shape. And we'll go ahead and label that f of x. Now we want to graph g of x equals 2x squared. Well, what happens if we multiply the function by 2? 2 is greater than 1, which means we have a vertical stretch happening here. I'm just going to hyphenate this because it's difficult to write with this mouse. So we have a vertical stretch happening when we multiply by 2. Essentially, every y value is being multiplied by 2 when this happens. So if you were to look at this point right here on the original graph, if its y value, if we said it was a y value of 1, well, what's going to happen to that y value? It's now going to become 2 because we are multiplying the y value by 2. So this point isn't going to move on the x-axis, but it is going to go up to here. And likewise, now that we said this y value is 2, then that means this point with a y value of 2 is going to get multiplied by 2 and become 4. So it's going to go up to here. The same thing is going to happen on the left side. This point right here is going to go up to 2, and this point at 2 is going to go up to 4. What's going to happen? The graph is going to look like this. It's going to become vertically stretched. We took all of our y values and pulled them upward. If we had any y values, or points that is, below the x-axis, they would have been pulled downward. They are getting pulled apart. Okay, from here, let's go ahead and graph h of x. Before we do, I should quickly label. This is g of x. It's always good to label these graphs. So h of x is 1/2 x squared. So what's going to happen to this point with the y equals 1 that we talked about earlier? Well, when we multiply it by 1/2, that means we are going to get a vertical shrink. So this point with a y equals 1 value will become y equals 1/2. It's going to move down here. And this point, again, when we said y equals 2, is now going to become y equals 1. All of the y values are getting pushed toward the x-axis. It's getting flattened out. So it's going to look like this. Notice all of your y values are now shorter than the original black graph that we had here. And this is our graph of h of x. This represents a vertical shrink or vertical compression because 1/2 was between 0 and 1. Okay, now as I mentioned, the next example will be a bit more complicated to show that a certain thing we're seeing here isn't actually happening. And that certain thing that you may have noticed is in the vertical stretch, it looks like the graph got narrower from the original. And in the vertical compression or shrink, it looks like the graph got wider from the original. That is not actually what's going on here in terms of vertical stretches and compressions. It is what's happening in this particular example because the graph of x squared is one of those very particular cases where a vertical stretch and compression are very similar to a horizontal stretch or compression on the same graph. So we have to show with this next example that that is just a big coincidence that that's happening. It will not always work out like that. So with that in mind, in this example, I want us to vertically stretch the following graph. I want you to take a moment, pause the video, see if you can't take your best guess at what will happen when you vertically stretch this graph. Okay, so let's try this together. Remember, when we vertically stretch, we are pulling all of our y values up and down. And anything on the x-axis is going to stay exactly where it started. So that's where we should start off. These x-intercepts here, here, and here are not going to move. From there, what's going to happen to this hill? Well, it's going to get pulled upward because it's getting vertically stretched. It's getting pulled away from the x-axis. And then this valley is going to get pulled downward, again, away from the x-axis. So it's going to look like this. From there, what's going to happen to this part of the graph on the right? Well, over here, if it's getting pulled away from the x-axis, that means the graph is going to look like this. And then on the left, if it's getting pulled away from the x-axis, the graph is going to look like this. All of the points are moving down here. All of the points are moving up here. But notice, none of these points moved their position on the x-axis. Only their y values were affected. The graph did not get any narrower or wider. So it is very important to remember vertical stretch and vertical shrink or compression has nothing to do with your x values being changed, only the y values. Alright, so for our last few examples here, I want us to combine all of the transformations we've learned into one process to find a decent sketch of a graph that is more complicated than just one transformation happening. So for this example, I want us to graph f of x equals negative times the quantity of x minus 3 squared plus 2. And we have a process to go about this, an order that we should follow. The first thing we should always do is make note of what the parent function is. So in our list of transformations, the parent function should always come first, and the parent function in this case is x squared. We are dealing with a parabola in this problem because of that square. The most common mistake with these types of problems is saying that the parent function is x. That should basically never happen. In order for the parent function to be x, you'd be dealing with just a basic line. So you should never say that your parent function is just x. It should always be an exponent involved, square root, an absolute value, things like that. From there, step 2. Just like order of operations, we should always go to multiplying next. So we are multiplying by a negative or a negative 1. That means we have a vertical reflection. Remember, whenever you multiply a negative on the outside of your function, notice the negative is not inside the square. That means it's vertical, and the negative represents a reflection. We are not multiplying by any number other than 1, though. It's a negative 1 technically. So that means there is not a vertical stretch or compression. So we can move on to the next step, which is addition and subtraction. It doesn't matter which of these you take care of first. I like to go left to right though. So the leftmost one is this negative 3. Because we are subtracting 3 inside of the function, it's going to go to the right 3. And from there, because we are adding 2 on the outside of the function, it's going to go up 2. And with this, we now want to graph all of these in the same plane, showing each transformation one at a time. The only 2 that you should ever combine into one step is the shifts. Shifting right, left, up, down. You can take care of both of those at the same time, but otherwise you should show every single step separately for your proper work on these problems. So the first graph is x squared. That's just a standard parabola. Now we want a vertical reflection in red. So remember, that means the x-axis is a mirror. We're going to flip this entire U upside down, keeping the same general shape we had before. And now we need to shift it to the right 3. So 1, 2, 3. We'll take our x-intercept and move it here. And now redraw the last graph that we had. And finally, we shift up 2. So we'll go up 1, 2. We'll take that last point that we had, redraw it, and then redraw that same U shape we had before. And this graph in blue or purple is the final graph. This is what the function looks like. This is f of x equals negative times the quantity of x minus 3 squared plus 2. All of these are just the steps to prove that this is the final graph. So notice we didn't have to plug in a single point, and plugging in points would have actually been pretty complicated in this. We'll actually talk about how to graph a parabola like this problem in future sections in some courses. And in this case, it would have been a very difficult problem to just start guessing random points to plug in, but instead we're able to just get a general idea of what this graph looks like just from sketching it. So from here, let's go ahead and try this last problem. I want you to take a moment, pause the video, see if you can't graph g of x equals 4 plus 2 times the absolute value of x plus 1 using this transformation method. Okay, so trying this together, the first thing we need is our parent function, which, notice we have absolute values. That means our parent function is the absolute value of x. From here, we go to multiplying. We're multiplying that absolute value function by a 2. It's a positive 2, which means there isn't a vertical reflection, but there is a vertical stretch. Remember, it's a vertical compression if the number is between 0 and 1. From here, we now go with addition and subtraction. And again, it's a good idea to go left to right. We are adding a 4 to the outside of the function. You could rewrite this if you preferred as a plus 4 over here instead of a positive 4 over here. Either way, that means the function is being shifted up 4. And finally, the plus 1 on the inside means that it's going to the left 1. So if we start graphing this, our parent function is the absolute value of x. That looks like a v. And remember, these are just rough sketches. They don't have to be perfect. Now we have a vertical stretch. So all of our y values are getting pulled away from the x-axis. So this graph is going to get pulled up like this. And from here, it's being shifted up 4 and left 1. So I'm going to show you that you can do these two steps in one if you prefer in this example. So we're going to shift up 4 and left 1. So taking this point, we will now have a point up here, and then we will redraw the same shape we just ended with, this longer V shape. And we always want to note what the final function is. So this v here is our function g of x, and this is what the graph of 4 plus 2 times the absolute value of x plus 1 looks like.